Okay, welcome back for more of elementary data structures. Today we're going to look at a queue, and I'd like to remind you at this point to just somewhere, maybe in your notebook on a sheet of paper or something, just have with you sort of a cheat sheet of, for example, what we've covered so far. So you should have each data structure that we've talked about. So far we've talked about a stack, what operations it can do. So for example, we had push and pop, and keep track of how efficient it is, depending on what implementation you use. So for example, we talked about a fixed size array, and in that case, we can implement push and pop in constant time, but the downside is that if this is a fixed size array, so if we run out of room, we don't have anything else to do except for throw an exception. And then in the last video, we also talked about an extendable array. So in that case, we're free in the sense that we can add more elements if we need to. We can extend the array. But depending on which strategy we use, changes the running time. So we saw that if we use, for example, the incremental strategy, we saw that push was linear time and even had an amortized linear time running time. But if we use the doubling strategy, then we can do this in amortized constant time. And the same thing for pop. We didn't get into that, but we can decrease the size of the array appropriately too. So stack, we can implement in a fixed size array, push and pop, all operations in constant time. We can use an extendable array, and our push and pop operations, as long as we're using the doubling strategy, has amortized constant time. All other operations size is empty or constant time. So just keep kind of on a sheet of paper somewhere what data structures we've talked about, what operations they can do, and how efficient those operations are. Okay, so on to a queue. So a queue, again, this is an arbitrary container which can store any objects. Oops. So this is another container that can store arbitrary objects, but it follows the first in, first out scheme. So you can think of this as a queue of people, a line of people at the DMV, for example. When a person arrives, they are n-queued, they're inserted into the end of the queue at the end of the line. Okay? And when a person is served, they're d-queued, they're removed from the front of the line. So this is the first in, first out scheme. So the main operations that this supports is we have that when you n-queue, this inserts at the end of the queue, at the end of this. When we d-queue, we remove and return whatever this front item is. And we can also support front. So this will return whatever this item is in front without actually removing it, like what d-queue removes that item and returns the item. Front will just return that element without removing it. And as with everything else, every other data structure we're going to talk about, size and isEmpty are supported. So this is just returning the number of elements that are stored in the container, and then true or false, are there no elements left in the container. We can always implement size and isEmpty in constant time by maintaining a counter. Every time we add an item, we increment the counter. Every time we remove an item, we decrement a counter, where the counter is initialized to 0. So size and isEmpty are no problem. We can always implement them in constant time. So what can we do with a queue? There's plenty of applications for queues, such as waiting lines, like I mentioned in the previous slide. This can also be used for multi-programming, which is a way of achieving a limited form of parallelism, even on a computer that has only one CPU. So this can be done by using a queue to keep track of whose turn it is to use system resources in a sort of round-robin protocol. So indirectly, queues and all of the other data structures that we'll see can be used either as an auxiliary structure, an auxiliary data structure. So this means that this is an algorithm that doesn't necessarily take a queue as an input or return a queue as an output, but instead, in order to perform some task, it's easier to kind of create one internally to that algorithm, work with it, and use that in order to perform some task. It can also be used as a component of other more complex, larger data structures. So think for a moment, how would you implement a queue if you had to write one? You might have done this for CS2, in fact. So how would you implement one? We could use an array like we did with stacks, but this would introduce a little bit of difficulty for us as we'd have to wrap around circularly to the array to appropriately insert and remove items. So instead, we're going to look at how to do this with a singly linked list. So a singly linked list consists of a sequence of nodes. So this is one node. We have each node stores some element. So this is whatever arbitrary object we're storing. And it also stores a pointer to whatever the next node is. So our singly linked list contains just a sequence of these nodes. The sequence can be traversed only in one direction from the head node, so we maintain a particular pointer that this is the first item in our singly linked list. And we have another pointer for our tail node, so this is just pointing to the last element in our list. And we can traverse this from the head to the tail. So if we start at the head, we can follow this next pointer, the next pointer, the next pointer, in order to traverse everything in our list. So let's see how we would use a singly linked list in order to implement a queue. So we have the front of our list, of our queue, is just the first item in our singly linked list, and the end of our queue is the last item of our singly linked list. So we have the front is stored at the first node and the end is stored at the last node. So when we enqueue an item, we want to add a new item. Let's say this is the new item that we're enqueuing. We create a new node, we store whatever our object is here, and we set the next pointer to be just a null pointer, right? So this is the new node that we've created. We called enqueue, right? We called enqueue for this object, let's call it X. So we're going to set, now we know what the old end was, we can set the next pointer for that end object to be the new object that we created. And because we've just created this node when we enqueued it, we just created it, we'll set now the end pointer to reference that last node instead of the previous last node. So we can enqueue in constant time this way. We just have a constant number of pointers that we have to update. Let's see how we would dequeue. So we want to remove from the front of our list here. So we're going to remove this item, but before we remove it, we're going to keep track of what was the next thing that it was pointing to. Because whatever this item is, once we remove the first item A, we're going to update the front pointer so that it instead references this one. That will be the new front. And then we can take this entire node and return that. So this is how we would enqueue and dequeue. Again, dequeue here is constant time. We have a constant number of primitive operations. We're just accessing what this next node is, reassigning the variable front to be whatever that next node is, and then returning this object. So enqueue and dequeue we can implement in constant time. The amount of space that it uses is dependent on however many elements that we have. Size and isEmpty we can implement in constant time always. We can also implement front, the function, just returning what this item is without removing it in constant time, just by returning whatever the front pointer references. So how would this change if we were to modify our implementation a little bit and enqueue from this direction and dequeue from this direction? So what we have right now is a good implementation. This is constant time operations for everything. So think for a moment, how would this change if we were to swap where enqueue and dequeue are? So if we want to enqueue, for example, we create a new node here. We'll store here whatever item we were enqueuing, and we can update its next pointer to be whatever front is pointing to, and then we can update this front pointer to be referencing whatever the new item that we just added was. So enqueue we can do in constant time still. But dequeue becomes a little bit more difficult, because when we dequeue, now we know we're going to return this item whatever end points to, so we can access this item D, this last one, in constant time, but the problem becomes updating this end pointer. So we can kind of save this off, remove this. We will return this ultimately, but in order to make this continue to work so that next time we call DQ we know what the end item is, we would have to update what this end pointer is. And we don't have anything going back from this item. We don't have this because this is just a singly linked list. Right? So if we wanted to update this end pointer, we would have to start at the beginning, at the front, go to the next item, and then the next item, and then the next item until we found that there's nothing else left, that we were back at our starting point. Then we can update our end pointer to that item. So DQ, if we were to implement it this way, would be linear time. So this wouldn't be an efficient implementation of a queue if we were using a singly linked list. Right? Much better to use singly linked list here because we can implement all operations in constant time, and singly linked list uses a little bit less memory than if we were to add additional pointers. So stacks and queues limit where items are inserted and which items are removed when we remove an item. So we're going to move now to data structures which can store arbitrary objects anywhere. So a list maintains objects order with respect to their position. So this lets us to view an ordered collection of objects in terms of their places without worrying about the exact way those places are represented. So the position of an object is the node which is storing that element. That way every object knows who comes before it and who comes after it. So this will allow us to insert at the beginning, at the end if we want, anywhere in the middle. So all operations are position based, right? And again, the position is the node which is storing that element. So for example, we can, given a position, check to see if it's the first one or the last one, or return, this is the first position of our list, the last position of our list, or check to see, given a position, what is the position that comes before it, or what is the position that comes after it. So again, all operations are position based. Or if we are updating our list, given a position and a specific element, we can replace whatever was stored at this position with whatever the element that we provided is. Or given two positions, P and Q, swap whichever elements are stored at each one of those positions. Or given a position, insert a new item, this is that element we're inserting, before this position, or insert it after that position. And as sort of a shortcut to insert before the first position or insert after the last position, we have insert first and insert last. So this will create a new element, which will be the first one, or a new element, which will be the last position. And then given a position, remove it. So again, all operations are position based. So let's see how we would implement this. So we could implement this quite naturally with a doubly linked list. So again, nodes themselves are acting as a position. So a node in a doubly linked list has a pointer back to whatever the previous position was, next to whatever the next position is, and then the middle item here, this is just storing that arbitrary object, whatever it is, at this part. And we have special nodes which are the head, so this is pointing to whatever the first node is, and tail, which is just pointing to whatever the last node is. Okay. So how would we implement, let's say, insert after? So let's see how we would do that. Note that because we have a doubly linked list, we can traverse beginning from the front and kind of working our way from the head to the tail, because each one of these has a pointer to the next. Or we could start at the tail and go to the previous one, and then the previous one, and then the previous one. So this can be traversed from either direction. This will be helpful because we want to perform some operations based on the node that comes before or the position after. So let's say we were inserting after position P this new element X. So again, we are given that position. We don't have to search for it. We're given already this is that entire node, so we can work directly on it. So we're given this position P. We can find for this position what is the node that comes after this position, because we'll have to change its references too. So we can do that in constant time just by following this pointer. And what we're going to do is we create this new node X, which is going to store our element. And we'll set the node which should come before it is that node P. The node that should come after it is whatever had come after P before this. And P's next node should now be this new node. And this other node, let's say C, its previous node should now be this new node that we added. Okay? So we have just a constant number of pointers, of references that we have to update. So insert after a given position, this is a constant time operation using a doubly linked list. Remove, so we're given a position, so we already immediately have access to this entire position, this entire node. We're not looking for it, we're given that as an argument. So we want to remove this node, and let's just say we're removing the last node, but this could be anything. So we can find, given this position, we know which item comes after it already, and we know which item comes before it. Right? So for the item that came before it, we'll set its next pointer to reference our new node. And for the item that came, this is for inserting. For removing this, we'll set the next pointer for the item that came before it to be whatever node had come after our position P. And for the one that came after it, we'll set its previous pointer to be whatever had come before that position P. That way we're effectively removing this entire position P. There are no other references to it. Okay, so this is a list implemented by a doubly linked list where all operations are position based, and we can implement all operations in constant time. So let's move on now to a vector. So a vector stores arbitrary objects based on their rank. So rank here, this is the number of elements which precede an item. So let's say we had a vector that had a few items in it. Let's say this was the first item, the second item, third, and fourth item. Okay. So the rank of this would be 0 because there's nothing that comes before it. The rank of B would be 1 because it has one item coming before it. The rank of C would be 2, and of D would be 3. Okay. So having rank-based operations will be convenient for particular tasks like sorting a collection of objects. We'll see later that sorting using rank-based operations makes sorting easier, more efficient than if we were using position-based operations. Similarly, there are some problems that are easier when we can use position-based operations rather than rank-based operations. So it's nice to have these two different ways where we can store an arbitrary collection of items, insert items wherever we want, remove items from wherever we want, but we have access to them using either a position, like when we are using a list, or by rank, as when we're using a vector. So with a vector, we can find how many items are in this vector. Are there no items in this vector? Return a specific element which is at a set rank. Given a set rank and some element, replace whatever we had stored at this rank before with whatever this other element is. Or given a rank, insert this new element at this rank. Now note that when we do this, let's say we wanted to insert E, let's say at rank 2, we want to insert this new element E into the vector that we had before here. That means when we're done with this operation, E should have rank 2. So we'll have to squeeze E right here so that it has rank 2, but that'll change the rank of all of the items that were coming after it. Okay? Because now we have one new item coming preceding those elements. And remove at rank, which is given a particular rank, remove whatever item was there. So let's say we removed the item at rank 2, we get rid of this item E, and now that changes the items that were coming after it. They have one less item coming after them. Okay. So let's see, how would we implement this? You might have noticed already how nicely this rank maps to an index for an array. So an array is actually a pretty efficient implementation for this vector data structure. So we use an array of some particular fixed size. We use a variable n to keep track of this is how many items are stored in our vector, so the number of elements stored. Then we can implement, for example, element at rank, at a specific rank, in constant time, just by returning whatever item is stored at that index in our array. So element at rank we can do in constant time. Insert at rank. So this is, we want to insert this new object O, and when we're done, it should have rank R. So it should have R items coming before it. So using an array, we have to find where that rank is. We can find where the rank is in constant time, just using access at index R of our array. But the problem is in changing the rank of all of the elements that come after it. So in order to kind of make room at this position for the new item we want to place there, we have to shift over all of these other items over by one position to make room for it. Okay? And if we insert, let's say at the very beginning, we have to shift over all n items. If we insert at the very end, this would be easy that we don't have to shift over anything, right? So inserting at any arbitrary rank, this operation takes linear time because in the worst case we have to shift over that many items in order to make room for this new one. Now note that we could use an extendable array also, just like we did with a stack, so we can grow the size of our vector as we need to, and this won't change the running time of our operations here either. Let's see also remove at rank. So given a specific rank, we want to remove an item. So again, we can access where that rank is in constant time. We can access the item we want to remove just by accessing the element at index R of our array. But once we get rid of this, we have to change that all of the items that come after it now have one less item preceding it, so their rank has to decrease. So using indices as a representation of rank, that means that we're going to move all of those elements over to the left by one position. And again, in the worst case, we have to move n elements over, which means shifting all of them down by one. One shift is constant time, but we might have to do this for n elements. So in the worst case, remove at rank also is linear time. So again, keep track somewhere on a sheet of paper, just a list of each data structure we've talked about. We've talked about stack and a queue, list, and now a vector. And just keep track of what operations can be performed for that data structure and how efficient they are. Constant time, linear time, etc. This will be a good reference for you. Okay. Now, a sequence is just a generalized data structure that supports all methods that we had from a vector and a list, which means that elements can be accessed from their rank, like we did with a vector, or position, like we did with the list. And how we would implement this would be either we could use an array or we could use a doubly linked list, whichever way we implemented vector and list. And you'll notice that those operations which are rank-based, an array is better suited for. Those operations that are position-based, a list is better suited for. So there's only a few instances in here where the runtime would be more efficient for an array or a list, and I want to point out those here. So, for example, at rank, rank of, or element at rank. So these are all rank-based operations. With an array, we immediately have access to, for example, element at rank, and we can do that in constant time. But with a list, because we're not maintaining that rank, we have to move over n positions even to just count up if we want to find an element at a particular rank, to move over, say, n positions to find the element at rank n. So this is slower for a list. This takes linear time for a list. Replace at rank. Again, this is another rank-based operations. Arrays can handle accessing an element at a particular rank easily, whereas a list, this is not so efficient because we have to move over n positions in order to find it. But inserting after or before a particular position, we can do this very efficiently with a list because remember, this is just updating a constant number of references. We're given that position already, we just insert an item before it or after it, and we update the pointer's previous index. But with an array, when we insert an item, we have to shift items over in order to appropriately update their rank of all the items that come after the item that we inserted. And similarly for removing, we can remove efficiently in constant time from a list because we're given that particular position already. We just update a constant number of references. But if we remove from an array, again, we have to decrease the rank of all of the items that came after it, and in doing so we shift over those elements that came after it, we shift them to come earlier, and doing that takes linear time. So there are some instances where you'd want to use an array to implement a sequence, and sometimes where you'd want to use a list, and that's all dependent on which of these operations you're going to perform, right? So let me do kind of a short example here. Let's say we wanted to call, let's say we knew we were going to write a program, and based on what we were doing, we knew we were going to make, let's say, n squared calls to replace at rank, and we were going to make another, let's say, n calls to insert after. Given this, which data structure should we use? Well, if we used an array, we'll call replace at rank n squared times, and the cost of replace at rank is constant. So I'm thinking of what the total cost of this is going to be, knowing that I'm going to make this many calls to replace at rank and this many calls to insert after, using an array. So the cost of all the calls to replace at rank and the cost of all the calls to insert after, we have n of them, and if we're using an array, this costs n. So our total cost here is big O of n squared. Now let's say we were using a list. We call replace at rank n squared times, but using a list, each call to replace at rank is linear, and then we make another n calls to insert after, which is more efficient on a list. This is constant time. So our total running time here is n cubed. So in that case, it would be much better for us to use an array-based implementation. Right? It just depends on which of these operations you're using, if you're using rank-based ones or position-based ones. Okay, if you have any questions, again, please post on Piazza anytime. I will get back to you as soon as I can, or maybe another student knows an answer to your question immediately, so don't hesitate to post on Piazza if you have any questions. See you in the next video.